Hi everybody, today we're going to talk about a graduation project in Faculty of Engineering at Ain Shams University. The project title was Design Implementation of a Solar Chimney Prototype that was under supervision of Energy and Renewable Energy Program. Before we start, we need to know what is a solar chimney. It's considered as a renewable energy power source that is environmentally friendly. It depends on the sun irradiance to create an updraft flow of wind energy. What is needed to build a solar chimney? The components are very simple. Number 1 is the updraft tower, usually made of steel, but PVC could be used for small prototypes. Number 2, solar collector, made of transparent glass, polycarbonate sheets is preferred. Number 3, power conversion unit, that includes a wind turbine coupled to an electric generator. As we mentioned before, that a solar chimney consists of an updraft tower, solar collector, and a wind turbine. The working process depends on the greenhouse effect by using the solar irradiance falling on the collector and transmitted to the ground. The solar irradiance would heat up the ground and consequently the air above, raising up its temperature and causing the density to decrease. The tower of a chimney is usually very high, up to 200 meters in an industrial scale, with the height the air above the tower used to have lower temperatures and densities. But due to heating up the air in the bottom flowing under collectors, the density of the air down is still lower than above. That makes a clear difference in density, and don't also forget the difference in pressure due to height. All these differences are enough to make a forced updraft flow inside the tower passing through the turbine that could generate power using wind capture. Design and numerical modeling. Well, to start our design, we started our approach using ANSYS Fluent to run a simulation for a solar chimney and rate its performance based on the value of the solar radiance. The setup used during the process was well studied upon a detailed survey about several solar chimneys that was simulated by approved researchers on Science Direct Journal. After validating the simulation, a fine mesh was applied to the model. Then we started running several simulations to find the optimum dimensions for the prototype and see the effect of these parameters, and it was found that increasing the height of solar chimney will increase the flow, which means more power. Increasing the diameter of each collector and tower increases the flow too, but there was an optimum point reached it for both. That after this point, the theory is reversed. Another modification was added on the tower as a diffuser with specified dimensions, as during our trials on ANSYS Fluent, we figured that adding a diffuser will make a suction pressure that increases the mass flow rate, but would have a slightly bad effect on the uniformity of the speed. Fortunately, the increase of power was significant. That was a point in our favor. And there is a sample for the diffuser effect on the chimney with 7 meters height and 3 meters collector diameter and 0.5 meters tower height diameter, shown in these figures. Our prototype was implemented on the acoustics building roof. The project had to be placed between 4 concrete columns, and the location was also recommended by consultative civil engineers to carry the weight of the project. Due to area restrictions upon the selected place for the location of the roof, the parameters of our design were the tower height was 7.1 meters, collector diameter of 3 meters, tower diameter of 0.5 meters, a collector height of 0.2 meters with an increasing slope to 0.3 meters, and the inner duct between the collector and the tower. And after all these trials, we started to add a horizontal axis wind turbine to our simulation and see the effect. The turbine was designed upon the energy speed of the system, which matched it with a midday clock. A combination between two boundary conditions was set to simulate both flows, the one inside the chimney due to irradiance, and the one that defines the rotating fluid upon the turbine, considering the turbine blades as a wall. Several airfoils, diameters, and locations for the turbine were tested during a safety simulation to verify the best power coefficient for the turbine with a suitable flow, and the Nipler 63 airfoil was suitable with a turbine diameter of 0.46 meter that would be fitted inside an 0.5 tower diameter after achieving a power coefficient of 0.31 and getting a Reynolds number on the blade surface in the specified region characterized by the selected airfoil. We also recommended installing the turbine at a height of 1.5 meters from the bottom, just in order to make it accessible for maintenance by adding a window in the tower that could be opened to install the turbine. Regardless that installing the turbine above just before the diffuser gave us better results regarding the power coefficient. That's a bad point. The final design that was agreed on, a 7.1 meters tower height, 3 meters collector diameters, had achieved upcoming results. Without the turbine, a mass flow rate of nearly 0.6 kg per second, and a velocity inside the chimney of 3 meters per second. And after installing the turbine, the mass flow rate of 0.43 kilograms per second achieved, and the velocity varies from 1.5 to 2.3 meters per second along the chimney, and a power coefficient of 0.31 for the turbine. It's normal to have the amount of reduction in the mass flow rate due to turbine solidity and the extracted power from the turbine due to energy capture. Implementation. Before heading to the manufacturing process, every part should be designed accurately to avoid any surprises, and we can't leave something to coincidence, as once we start, there's no room for mistakes. Sending a plan for each of our procedure put us on the right track, and there we had 3 plans agreed on, one for designing and detailed workshop drawings, and one for manufacturing, and the last for installing the product. All of us were aware about the time schedule, so we had to work in parallel with all these plans to coordinate the timing with the workshops, the crane, the contractor for the reinforced concrete base, and the doctor at the college, and when all these 3 plans will intersect. Before driving into details, we must mention that we have succeeded in securing funding for the project implementation with 53,000 Egyptian pounds under the cover of Academy of Scientific Research and Technology, and agreed with the Petrojet company as a contractor for the manufacturing process, so we can manufacture the tower at the workshops. Must mention that Petrojet is one of the best oil and gas towers manufacturing in the Middle East. 1. Design and workshop drawings. An inventor-to-desk program was agreed to work on for the project design of mechanical parts and provide workshop drawings. A. Collector frame to carry the glass. The collector frame was octagon-shaped, inspired by spiderweb shape. It was manufactured using hollow square cross-section rods that was welded together to make a quarter, and with 4 symmetric quarters collected together using bolts, the collector frame would be ready. B. Tower, which was agreed to be designed and manufactured in 4 parts for easy transportation and fixation. Those parts are a base, 2 parts each 3 meters tall containing rigs, and a small diffuser part. All these parts will be collected together using bolts, as each of them contains a flange that was considered while designing. C. Turbine. Turbine was designed as mentioned before using ANSYS Fluent based on the flow inside the tower. Bearing housing of the turbine was designed using inventor-to-desk, specifying the shaft diameter and locating 2 SKF ball bearing. Then 2 couplings were designed for connections between turbine, shaft, and the generator. The bearing housing was designed with 4 threaded holes shifted with 90 degrees and said to be located in the middle of the tower, using 4 rods threaded into the 4 holes of the bearing housing. D. Agreeing with the contractor to start design of a square reinforced concrete base with a side length of 3.1 meters and set the required thickness and the number of anchor bolts required to carry the tower, informing him that we have handed over the drawings to the workshop, and they ensured that the weight of the tower would be from 700 to 800 kilograms. We also asked him to set the best point on the roof where the project could land safely and displays that design on a consultative office that had signed the papers and approved that all this work is true and applicable. We also added 4 eye bolts on each corner of the base to reinforce the tower with steel tension cables. And here we have come to the final part of the design. To approve that final design, we had to cover the connection area between the tower and the collector frame to avoid any heat losses during the operation. So a metallic cone was designed to be collected with the frame using bolts. Number 2. Now we can proceed to the manufacturing process in the workshops. Number 1. All metal parts which were the collector frame, the shaft, and the bearing houses and the tower. Number 2. The turbine blades that were made of PETG using 3D printer as a blade were only 22 centimeters long. 3. Turbine nose that was made of aluminum for less weight. All these parts were manufactured in workshops using center lace, milling machine, and a rolling machine for tower parts, where metal sheets were rolled then welded, and the final product was painted gray. Number 3. Installation. Now we can start the action. We started setting an appointment between the college and the contractor to start implementing the reinforced concrete base, after they informed us with the required thickness that was 30 centimeters with 8 anchor bolts of M16 to carry the tower. The supplements, repa, sand, gravel, and concrete were carried out to the roof using a Blanco crane, then getting the job done up there, and after 7 days, the base was ready to bear stress and carry on the tower. We also had to thank engineer Ahmed Higazi for setting up a rigging plan, a lifting plan, and a transportation plan that was necessary. As I mentioned before, there is no room for mistakes now. We are not playing anymore. Now we have come to the welcome party, the day where everything was set to be completed. Now we can see every part at its original place. We started setting an appointment with the crane contractor, the workshop, and the cottage, all in one, and we specified a day for transportation and for the fixation of the tower with the crane. The specified time was midnight, as no crowd would be in the streets, so the package could be transported rapidly and easily. We started transporting the tower and the frames from the workshop to the cottage being carried on the transport vehicle, and the crane also attended to meet at the same time by the cottage. The outside facade of the Cotostix building helped us a lot to set the best location where the crane can spread his arms, and then we started the action. Collector parts were lifted first to the roof, then the base of the tower, which was carried and fixed on the anchor poles of the concrete base. The three remaining parts of the tower were collected on the ground and then lifted horizontally, as there were two sides of a hinge, one on the second tower part and the other on the tower base part. These sides were constrained together and a stop bolt was fitted in, locked by nuts, to lock the hinge. Then we started bodying the other side of the tower till the tower stood vertically. The next day, a carpenter came on taking on the measurements of the glass bars for each quarter and the window of the turbine, and after 2 days, the glass was carried on the frame. The turbine with its housing and generator was finished also, collected and implemented in the 2 days of glass waiting. Now the project is 100% done and certified, and it operated successfully. After implementing the project, now we can dive into experimental work and comparing results. First, the wind speed inside the chimney was measured after installation from midday to the sunset. The velocity was measured each hour to perform the performance curve of the chimney with a height of 7.1 meters, and the average speed is 1.4 meters per second. After comparing the results between our numerical study and experimental work, we can say that this deviation is not high, maybe due to heat loss on materials used, so there will be modifications for more efficiency. Must also mention that our simulation didn't consider the outside wind and its effect on the simulation, as it increased the flow inside the tower up to 2.8 meters per second several times while taking on the measurements, and that illustrates why it also worked at night due to the outside wind. Another comparison for our results was the material of the absorber. 4 materials were used: 1 the black covering using plastic bags, 2 the aluminium, 3 the gravel, and the last was the concrete. Each was tested in one quadrant of the collector. The temperature of the materials was measured from midday to the sunset using an avometer. It was found that the black covering showed a great potential of storing heat for longer periods and reaching high temperatures than the gravel, but the aluminium tended to lose that heat rapidly as fast as it absorbs it. And now we have come to the end of the video. Thanks everybody for watching. Hope it was profitable, and don't forget, if you like this video, don't forget to like, subscribe my channel. See you soon in other videos. Goodbye everyone.
And 1,000 times I've seen this road, 1,000 times. I've got no roots, but my home was never on the